and welcome. Tonight, we'll drift through the cosmos together, exploring the quiet mysteries of life beyond Earth. Let your thoughts settle. Allow your breathing to slow. Close your eyes when you're ready, or let them rest half open on these words. Either way, you're exactly where you need to be. The universe contains more stars than grains of sand on every beach on Earth. When you look up at the night sky, you're seeing only the faintest fraction of what exists. Our Milky Way galaxy alone holds somewhere between 100 billion and 400 billion stars, each one a burning sphere of light scattered across unimaginable distances. Beyond our galaxy, astronomers have identified roughly 2 trillion other galaxies stretching through the observable universe. Within that immense expanse, the sheer number of stars becomes almost impossible to comprehend. 200 billion trillion stars, give or take. Each one represents a potential solar system. Each system might harbor worlds, and on those worlds, the conditions for life could quietly unfold in ways we're only beginning to imagine. Scientists have discovered thousands of planets orbiting distant stars. These worlds are called exoplanets, and their existence was merely theoretical until the early 1990s. The first confirmed detection came in 1992, when astronomers found planets circling a pulsar. Since then, the pace of discovery has accelerated dramatically. NASA's Kepler Space Telescope alone identified more than 2,700 confirmed exoplanets during its mission. Today, the total count exceeds 5,400 worlds, with thousands more candidates awaiting verification. Each discovery adds another data point to our understanding of how common planetary systems truly are. The universe, it seems, is exceptionally good at making planets. Roughly 1 in 5 sun-like stars has a planet in its habitable zone. The habitable zone is that precious region around a star where temperatures allow liquid water to exist on a planet's surface. Water, as far as we understand life, is essential. It serves as the universal solvent, the medium in which complex chemistry can unfold. When astronomers analyzed data from the Kepler mission, they found that approximately 22% of sun-like stars host Earth-sized planets within their habitable zones. This translates to billions of potentially habitable worlds in our galaxy alone. Around 11 billion of these orbit stars similar to our Sun. The numbers suggest that habitable environments are not rare cosmic accidents, but common outcomes of planetary formation. Red dwarf stars are the most common type in the galaxy. These small, cool stars make up roughly 70 to 90% of all stars in the Milky Way. Though they burn dimmer and cooler than our Sun, red dwarfs possess remarkable longevity. Some will continue shining for trillions of years, far longer than the current age of the universe. Their habitable zones lie much closer to the star, meaning any planets there would orbit in tight, fast circles. Despite challenges like intense stellar flares and tidal locking, red dwarfs represent the most numerous opportunity for life to emerge. Their abundance means that even if only a small fraction host habitable worlds, the total number of such planets could be staggering. In the quiet red glow of these ancient stars life might find countless homes. The closest potentially habitable planet lies just over 4 light-years away. Proxima Centauri b orbits the nearest star to our Sun, a red dwarf called Proxima Centauri. Discovered in 2016, this world completes an orbit every 11 days, circling within its star's habitable zone. Its mass suggests it could be rocky, similar to Earth. However, the planet faces challenges. Its star emits powerful flares that could strip away any atmosphere. It's likely tidally locked, with one side eternally facing the star and the other trapped in permanent darkness. Still, some models suggest that with the right atmospheric conditions, liquid water could exist somewhere on its surface. If life has emerged there, it would be our nearest cosmic neighbor, dwelling in perpetual sunset or endless night, just 4.2 light-years from home. Water is the most important ingredient for life as we know it. On Earth, wherever liquid water exists, life has found a way to thrive. From the scalding depths of hydrothermal vents to the frozen lakes beneath Antarctic ice, water serves as the essential medium for biological chemistry. Its unique properties, including its ability to dissolve countless substances and remain liquid across a wide temperature range, make it irreplaceable for life's processes. When astronomers search for habitable worlds, they focus first on the presence of water. Recent discoveries have revealed water's ubiquity throughout the solar system and beyond. Ice exists on Mars, on Jupiter's moons, on comets drifting through the outer reaches. Water vapor has been detected in the atmospheres of distant exoplanets. The universe, it appears, is awash with this precious molecule, suggesting that one of life's most fundamental requirements is widely available among the stars. Europa, one of Jupiter's moons, hides an ocean beneath its ice. The smooth, cracked surface of this frozen world conceals something remarkable. Beneath a shell of ice, perhaps 10 to 15 kilometers thick, lies a global ocean of liquid water, kept from freezing by tidal heating. As Europa orbits Jupiter, the immense gravitational pull of the giant planet, along with the tugs from neighboring moons, flexes and squeezes Europa's interior. This constant motion generates heat, enough to maintain an ocean that may contain twice as much water as all of Earth's oceans combined. Scientists believe this hidden sea could be in contact with a rocky seafloor, allowing chemical reactions similar to those that occur at Earth's deep ocean hydrothermal vents. If life exists in Europa's dark waters, it would have evolved in total isolation from the Sun, sustained by chemistry and heat from the planet's core. Enceladus, a moon of Saturn, shoots geysers into space. When the Cassini spacecraft flew past this small, icy moon, it discovered something extraordinary. Enormous plumes of water vapor and ice particles erupt from cracks near Enceladus's south pole, reaching hundreds of kilometers into space. These geysers originate from a subsurface ocean, one that lies beneath a relatively thin ice shell. The material shooting into space contains not just water, but also organic molecules, salts, and even silica particles. Chemical analysis suggests the ocean is in contact with a rocky core, where hot water interacts with minerals. These are the same kinds of conditions that support life in Earth's deep oceans. The geysers effectively sample the ocean's contents, making Enceladus one of the most promising places in the solar system to search for life. No drilling required. The moon delivers its secrets directly into space, waiting to be caught and analyzed. Amino acids have been found in meteorites that fell to Earth. These organic building blocks of proteins have been detected in several meteorites, most famously in the Murchison meteorite that landed in Australia in 1969. Analysis revealed more than 90 different amino acids in its ancient rock, including many that don't exist in Earth's biology. The presence of these compounds in meteorites demonstrates that the chemical precursors for life can form in space, within the cold, dark environment of interstellar clouds and asteroids. Some of these amino acids show what scientists call a chiral preference, meaning they exist in specific molecular orientations that hint at chemical processes occurring beyond Earth. The discovery supports the idea that the ingredients for life are not unique to our planet, but are created through natural processes throughout the universe, then delivered to worlds via meteorite impacts during their early histories. Tardigrades can survive the vacuum of space. These microscopic creatures, also called water bears, are among the toughest organisms on Earth. Measuring less than a millimeter long, they look like tiny, eight-legged bears under a microscope. When conditions become harsh, tardigrades enter a state called cryptobiosis, essentially shutting down their metabolism and becoming dormant. In this state, they can survive extraordinary extremes. Scientists have subjected them to temperatures near absolute zero and as high as 150 degrees Celsius for brief periods. They can withstand pressures 6 times greater than the deepest ocean trenches, and radiation doses hundreds of times higher than what would kill a human. In 2007, tardigrades were sent into space aboard a satellite. Some were exposed to the vacuum of space and solar radiation. After 10 days, they were revived, and many survived, even producing viable offspring. Their resilience demonstrates that life, once it evolves mechanisms for extreme survival, can endure conditions far more severe than those on most planetary surfaces, expanding our sense of what's possible. Extremophiles on Earth hint at life's versatility elsewhere. These remarkable organisms thrive in environments once thought completely hostile to life. Thermophiles live in boiling water near volcanic vents, where temperatures exceed the boiling point. Psychrophiles flourish in Antarctic ice at temperatures below freezing. Halophiles thrive in salt concentrations that would kill most organisms. Acidophiles live in sulfuric acid pools, and alkaliphiles prefer highly basic environments. Radio-resistant bacteria can survive radiation doses that would instantly kill humans. Each extremophile demonstrates that life can adapt to conditions vastly different from the moderate climates we consider normal. These organisms expand our understanding of where life might exist in the universe. If life can survive in Earth's most hostile environments, Perhaps it can also exist in the sulfuric acid clouds of Venus, the frozen methane lakes of Titan, or the radiation-bombarded surface of Jupiter's moons. The building blocks of life are common in interstellar space. When astronomers study the light from distant gas clouds, they detect the signatures of organic molecules. Simple compounds like formaldehyde, methanol, and acetaldehyde float between the stars. More complex molecules have been found too, including amino acids, sugars, and even the components of nucleotides. These molecules form through chemical reactions on the surfaces of tiny dust grains, where thin layers of ice provide a substrate for chemistry to occur. Ultraviolet radiation from nearby stars provides energy to drive these reactions. The Rosetta mission, which studied Comet 67P, found glycine, an amino acid, along with phosphorus, an essential element for DNA and cell membranes. The cosmos is awash in organic chemistry. The same molecular building blocks that make up life on Earth are being manufactured throughout space, suggesting that the first steps toward life might be universal processes occurring wherever the right conditions exist. Mars may have once been habitable. Billions of years ago, Mars looked very different from the cold, dry desert we see today. Evidence from rover missions and orbital observations reveals ancient river valleys, lake beds, and possible ocean basins. The presence of clay minerals, which form in the presence of water, indicates that liquid water once flowed across the Martian surface. The planet had a thicker atmosphere then, enough to keep water stable and to trap heat. For perhaps the first billion years of its history, Mars might have been a world of lakes and rivers, with conditions potentially suitable for life to emerge. What happened to that water is a story of atmospheric loss. Mars's weak magnetic field could not protect its atmosphere from being stripped away by solar wind. Over time, the planet's air thinned, the water evaporated or froze, and the surface became the barren landscape we see today. But if life did arise during that early wetter period, it might still survive deep underground, where ice remains and where geothermal heat could sustain microbial communities. Scientists have detected methane in Mars's atmosphere. Methane is a simple organic molecule, but its presence in Mars's thin atmosphere is intriguing. On Earth, most methane is produced by biological activity, primarily by microbes living in anaerobic environments. Geological processes can also produce methane, such as when water reacts with certain rocks. The methane on Mars appears in varying concentrations, with levels that change seasonally. Several spacecraft and rovers, including NASA's Curiosity rover, have detected these methane plumes. The source remains unknown. It could be ancient methane trapped in ice, slowly seeping out. It could be produced by ongoing geological activity, or it could potentially be created by living organisms dwelling beneath the surface. Future missions aim to trace the methane to its source, which might finally answer whether Mars harbors or has harbored life. Saturn's moon Titan has liquid lakes, but they're filled with methane. Titan is the only world besides Earth where stable bodies of liquid exist on the surface. But these aren't lakes of water. Titan is far too cold for that. Instead, Liquid methane and ethane fill lakes and seas near the moon's poles, with clouds of these hydrocarbons drifting through a thick nitrogen atmosphere. Rainfall occurs, but it falls as methane, not water. Rivers carved by flowing methane drain into methane seas. It's a complete hydrological cycle, just based on entirely different chemistry. Despite the frigid temperatures of -179 degrees Celsius, some scientists speculate that life could potentially exist in Titan's methane seas, using a biochemistry completely unlike that on Earth. Such life would need to operate at extremely low temperatures and use methane as a solvent instead of water. It would be alien in the truest sense, following entirely different rules of chemistry. The Drake equation estimates how many alien civilizations might exist. Formulated by astronomer Frank Drake in 1961, this equation attempts to estimate the number of detectable civilizations in our galaxy. It multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life develops, the fraction where intelligent life evolves, the fraction that develop technology, and the length of time they remain detectable. The equation itself is straightforward. The challenge lies in the values. Most of these numbers are uncertain. Depending on the assumptions, the Drake equation suggests anywhere from one civilization, us, to thousands or even millions. Recent exoplanet discoveries have helped constrain some factors. We now know planets are common, and many orbit in habitable zones. But the other factors remain unknown. How often does life arise? How often does it become intelligent? How long do civilizations last? These questions remain unanswered, making the Drake equation more a framework for thinking about the problem than a precise calculation. The Fermi paradox asks why we haven't found aliens yet, named after physicist Enrico Fermi, who allegedly asked, "Where is everybody?" During a lunch conversation, the Fermi paradox highlights a contradiction. Given the age and size of the universe and the abundance of potentially habitable worlds, it seems likely that many alien civilizations should exist. Some should be far more advanced than humanity. If interstellar travel is possible, even at slow speeds, an advanced civilization could colonize the entire galaxy in a few million years. Yet we see no evidence of such colonization. We detect no radio signals, no megastructures, no signs of industrial activity on other worlds. The galaxy appears silent and empty. This silence demands explanation. Perhaps life is rarer than we think. Perhaps intelligence rarely evolves. Perhaps advanced civilizations destroy themselves before they can spread. Or perhaps they're out there, but haven't noticed us yet, or choose not to make contact. The paradox remains unresolved, a profound question mark hanging over humanity's place in the cosmos. The Great Filter might explain our cosmic loneliness. This concept, proposed by economist Robin Hanson, suggests that somewhere between the formation of a planet and the development of a galaxy-spanning civilization, there exists a barrier so difficult that almost no one passes it. This is the Great Filter. It could lie in our past, perhaps in the transition from non-life to life, or from simple cells to complex ones. If the filter is behind us, then we're extraordinarily lucky to exist, and life might be extremely rare in the universe. But if the filter lies ahead, then our future is grim. Perhaps civilizations inevitably destroy themselves with nuclear weapons, climate change, artificial intelligence, or some other technology we haven't yet developed. The Great Filter offers one explanation for the Fermi paradox, but it also carries a warning. If intelligent civilizations are common throughout the galaxy's history, yet none seem to have survived long enough to leave evidence, then perhaps we too face an insurmountable challenge. The silence of space might not reflect rarity, but tragedy. Scientists are searching for biosignatures in exoplanet atmospheres. When a planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere before reaching Earth. This light carries information. Different molecules absorb light at specific wavelengths, leaving distinctive fingerprints in the spectrum. By analyzing this light, astronomers can determine what gases are present in the planet's atmosphere. Certain combinations of gases could indicate life. Oxygen is a strong candidate, especially when found alongside gases like methane, with which it normally reacts. On Earth, oxygen exists because photosynthetic organisms constantly replenish it. Without life, Earth's oxygen would disappear relatively quickly. Other potential biosignatures include phosphine, dimethyl sulfide, or even industrial pollutants that would suggest technological activity. The James Webb Space Telescope and future missions are beginning this search in earnest, analyzing the atmospheres of nearby exoplanets for these telltale signs. The discovery of a biosignature would be profound, indicating that life has arisen more than once in the universe. Oxygen alone isn't enough to confirm life on another planet. While oxygen is produced by photosynthesis on Earth and would be a promising sign elsewhere, several non-biological processes can also generate oxygen. Ultraviolet light from a star can split water molecules apart, freeing oxygen. If a planet has lost most of its water but retains an atmosphere, it could accumulate oxygen through this photolysis process, creating a false positive. Another scenario involves planets that have lost their oceans entirely. Without water to react with, oxygen could build up in the atmosphere without any biological source. To avoid misidentifying these scenarios as signs of life, scientists look for additional context. The presence of other gases, the planet's temperature, the activity of its star, and the overall atmospheric composition all provide clues. A true biosignature would likely involve multiple lines of evidence, a pattern of gases and conditions that cannot be easily explained by non-biological chemistry. The search requires careful detective work, ruling out false positives to reach the truth. Seasonal changes in atmospheric gases could reveal alien life. On Earth, the amount of carbon dioxide in the atmosphere changes with the seasons. During spring and summer in the northern hemisphere, plants grow and photosynthesize, pulling carbon dioxide out of the air. In autumn and winter, plants decay, releasing carbon dioxide back. These seasonal oscillations create a detectable signal in atmospheric measurements. If similar cycles exist on another planet, They could indicate the presence of a biosphere, responding to seasonal changes in sunlight. Detecting these variations would require observing a planet repeatedly over time, watching for patterns that correspond to its orbit around its star. The presence of such cycles would be difficult to explain without biology, making them a potentially powerful biosignature. They would suggest not just life, but a thriving ecosystem, one active enough to influence the entire planet's atmosphere in measurable ways. Future telescopes, capable of sustained observations of nearby exoplanets, may eventually detect these subtle rhythms. Chemical disequilibrium in an atmosphere can hint at life. In a lifeless world's atmosphere, chemistry tends toward equilibrium. Reactive gases combine and neutralize each other until the atmosphere reaches a stable state. Earth's atmosphere is wildly out of equilibrium. We have oxygen and methane coexisting, even though they should react and disappear. We have other gas combinations that don't make sense without something actively producing them. Life is that something. Organisms constantly release gases through metabolism, maintaining an atmospheric chemistry that would otherwise be unstable. When scientists model early Earth's atmosphere, they find that even before oxygen became abundant, life's presence created subtle disequilibria. Detecting such imbalances on an exoplanet could indicate biological activity, even if we don't recognize the specific biosignatures. The key is finding combinations of gases that persist in ratios impossible to maintain through chemistry and geology alone. The atmosphere would essentially be confessing the presence of life through its perpetual chemical discord, a discord that only living processes could sustain. Panspermia suggests life might spread between worlds. This theory proposes that life, or at least its chemical precursors, could be transferred from one planet to another, perhaps even between star systems. The mechanism could be meteorite impacts. When a large asteroid strikes a planet, it ejects material into space. Some of this material, particularly from planets with thick atmospheres like Mars, could escape the planet's gravity and drift through space. If microorganisms were present in that material, protected within rocks, they might survive the journey. Experiments have shown that certain bacteria can survive in space for extended periods when shielded from radiation. Panspermia doesn't explain how life originally arose, but it suggests that once it begins somewhere, it might spread widely. If panspermia is common, then life might be more widespread in the universe than we'd otherwise expect. A single origin could seed countless worlds. Mars and Earth may have exchanged material throughout their histories. If life originated on one, it might have been transported to the other. We could, in a sense, be distant descendants of Martian microbes, or Mars could harbor Earth life carried there by ancient impacts. Complex molecules have been found in interstellar clouds. The space between stars is not empty, but filled with vast clouds of gas and dust. These clouds are cold, typically only a few degrees above absolute zero. Yet within them, chemistry occurs. Astronomers have detected more than 200 different molecules in interstellar space, including surprisingly complex organic compounds. Polycyclic aromatic hydrocarbons, ring-shaped carbon molecules are abundant. Sugars like glycolaldehyde are precursor to ribose, the sugar in RNA, have been found. Even amino acids and simple proteins precursors exist. These molecules form on the surfaces of tiny dust grains, where ice coats act as a substrate for chemical reactions powered by ultraviolet radiation. When new stars form within these clouds, they inherit this complex chemistry. The planets that form around these stars begin with a rich inventory of organic molecules already present. Life doesn't need to start from scratch. The universe has already done some of the work, synthesizing the building blocks through natural processes that occur across countless light years. Some bacteria on Earth tolerate high levels of arsenic. In 2010, scientists announced the discovery of a bacterium, GFAJ1, living in California's Mono Lake. This microbe thrives in water with high concentrations of arsenic, a normally toxic element. Initial claims suggested the bacterium might substitute arsenic for phosphorus in its DNA and other molecules, a finding that would have been revolutionary since phosphorus is considered essential for life. However, follow-up studies showed the substitution wasn't as complete as first reported, though the bacterium's remarkable arsenic tolerance remains scientifically interesting. This finding suggests that life can adapt to environments with elements typically considered toxic. If organisms on Earth can survive in arsenic-rich conditions, this expands our thinking about what chemistry might support life. Perhaps there are worlds where different elements play larger roles than we'd expect, or where life has adapted to chemical environments we'd consider impossible. Life might be more chemically flexible than we currently imagine, capable of emerging in conditions that challenge our Earth-centered assumptions. Deep-sea hydrothermal vents support life without sunlight. At the bottom of Earth's oceans, in total darkness, hot water erupts from cracks in the seafloor. These hydrothermal vents, discovered in 1977, were expected to be barren. Instead, they teem with life. Giant tube worms, eyeless shrimp, and unique bacteria cluster around the vents, forming ecosystems completely independent of sunlight. The base of these food chains is chemosynthetic bacteria. Instead of using sunlight for energy like photosynthetic organisms, they extract energy from chemicals in the hot vent water, particularly hydrogen sulfide. This demonstrates that life doesn't require sunlight, only a source of chemical energy. On other worlds, similar ecosystems could exist. Europa's subsurface ocean might have its own hydrothermal vents, powered by tidal heating. Enceladus shows evidence of water-rock interactions that could support similar chemistry. Even planets far from their stars, rogue worlds drifting through interstellar space, could potentially harbor life in subsurface oceans heated by their cores. Life needs energy, but that energy doesn't have to come from a star. SETI has been listening for alien signals for over 60 years. The search for extraterrestrial intelligence began in earnest in 1960 with Project Ozma, when astronomer Frank Drake pointed a radio telescope at two nearby stars and listened for artificial signals. Since then, SETI projects have expanded dramatically. Modern SETI searchers scan millions of star systems across a wide range of radio frequencies, looking for patterns that would indicate intelligent transmission. Some searchers focus on optical signals, watching for laser pulses. Others look for techno-signatures, evidence of engineering projects like Dyson spheres or industrial atmospheric pollution. Despite decades of effort and billions of channels searched, SETI has not yet confirmed a signal from an extraterrestrial civilization. This null result doesn't prove aliens don't exist. Space is vast, and signals take years to travel between stars. Perhaps we haven't searched long enough, or we're looking at the wrong frequencies, or civilizations communicate using technologies we haven't imagined. The search continues, patient and persistent, listening to the stars. The WOW signal remains unexplained. On August 15, 1977, a radio telescope in Ohio detected a strong, narrow-band signal that lasted 72 seconds. The signal was so unusual that astronomer Jerry Amon, reviewing the printout, circled it and wrote "Wow" in the margin. The signal came from the direction of Sagittarius and showed characteristics consistent with an artificial transmission. It was the right kind of signal SETI searchers hoped to find. Narrow band, far from any Earth-based frequency, and originating from deep space. But it never repeated. Despite numerous follow-up observations of the same region of sky, the signal has never been detected again. Without repetition or additional data, scientists cannot determine what caused it. Was it an alien transmission? A natural but rare astronomical phenomenon? An Earth-based signal that somehow bounced into the telescope? The mystery endures. The WOW signal represents both the promise and frustration of SETI, a tantalizing hint that might mean everything or nothing. Venus might have had oceans billions of years ago. Today, Venus is a hellscape. Its thick atmosphere traps heat, creating surface temperatures hot enough to melt lead. Sulfuric acid clouds shroud the planet, but Venus might not have always been this way. Some computer models suggest that early Venus could have been temperate, with liquid water oceans covering much of its surface, potentially for as long as 2 billion years or more. This depends heavily on assumptions about Venus's initial water content, rotation rate, and atmospheric composition. What transformed it into the furnace we see today appears to be a runaway greenhouse effect. Water vapor, a potent greenhouse gas, accumulated in the atmosphere. As temperatures rose, more water evaporated, trapping more heat. Eventually, the oceans boiled away entirely, and ultraviolet light split the water molecules, allowing hydrogen to escape to space. The planet lost its water and became locked in a permanent hot state. The possibility that Venus was once habitable adds it to the list of places where life might have originated in our solar system's history, though whether any trace of such ancient life could survive is purely speculative. Jupiter's moon Ganymede has the largest subsurface ocean in the solar system. Ganymede, the largest moon in the solar system, hides an ocean beneath its icy crust. This ocean is estimated to contain more water than all of Earth's surface water combined. Unlike Europa's ocean, which sits relatively close to the surface, Ganymede's ocean lies sandwiched between layers of ice. At the surface is regular ice. Below that, the ocean, and below the ocean is another layer of high-pressure ice, before finally reaching a rocky core. This ice-water-ice structure is unusual. Whether life could exist in such an environment is unclear. The ocean is likely cut off from the rocky interior, which might limit the availability of nutrients and minerals. Still, the sheer volume of water, combined with potential tidal heating from Jupiter's gravity, makes Ganymede intriguing. Any life there would exist in perpetual darkness, isolated between layers of ice, nourished by chemistry we can barely imagine. Phosphine detected on Venus sparked debate about possible life. In 2020, scientists announced the detection of phosphine gas in Venus's atmosphere, though this finding has remained controversial. On Earth, phosphine is produced primarily by anaerobic bacteria, organisms that live without oxygen, and it's challenging to produce through known non-biological chemistry under Venusian conditions. The initial detection raised the intriguing possibility that microbial life could exist in Venus's clouds, floating in droplets where temperatures are more moderate than at the scorching surface. The clouds contain sulfuric acid, which would be deadly to most Earth life, but adaptations to such extreme acidity aren't impossible to imagine. However, the detection itself has been questioned by multiple research teams, with some follow-up observations failing to confirm the phosphine signal. Alternative explanations have been proposed, including previously unknown chemical reactions or measurement artifacts. The debate remains unresolved, highlighting how difficult it is to interpret chemical signatures as definitive evidence of life. Venus has certainly rejoined the conversation about where life might exist, even if the phosphine question remains unanswered. Silicon-based life is theoretically possible, but faces challenges. Science fiction often imagines aliens based on silicon instead of carbon. Silicon sits just below carbon on the periodic table and can form 4 bonds like carbon does, which initially suggests it might be able to create complex molecules. However, silicon chemistry has significant limitations that make it less versatile than carbon. Silicon-oxygen bonds are much stronger than silicon-silicon bonds, meaning silicon readily forms rocks and minerals rather than the flexible chains needed for complex biochemistry. Silicon doesn't form stable long-chain molecules or double bonds as readily as carbon, which restricts the kinds of structures possible. Water is generally not a good solvent for silicon-based compounds, which tend to be insoluble. If silicon-based life exists, it would likely require a very different chemical environment, perhaps using liquid methane or ammonia instead of water, and operating at much lower temperatures. While carbon's versatility and abundance make it the far more likely foundation for life. We can't entirely rule out silicon chemistry under conditions vastly different from Earth. The universe is full of environments we haven't yet explored. Intelligent life might use non-radio communication. SETI focuses heavily on radio signals, but advanced civilizations might communicate using methods we haven't considered. They could use laser pulses, modulated streams of light that carry vast amounts of information and are harder to detect than radio broadcasts. They might employ neutrino beams, particles that pass through matter almost without interaction, making them ideal for long-distance communication, but requiring enormous detectors. Gravitational wave communication is possible in theory, encoding messages in ripples in space-time itself. Or perhaps civilizations abandon electromagnetic signals entirely, using quantum entanglement for instantaneous communication across distances. If they've moved to these exotic technologies, our searchers might miss them entirely. We're like someone trying to find the internet by listening to telegraph wires. The signals are there, but we're tuned to the wrong medium. This possibility humbles us. It suggests that the silence we detect might not mean absence, but that we're still too technologically naive to recognize the conversations happening all around us. The zoo hypothesis suggests aliens are watching us. One solution to the Fermi paradox proposes that advanced aliens know about us but deliberately avoid contact. Perhaps they observe humanity from a distance, treating Earth like a wildlife preserve or an uncontacted tribe. Their reasons might be ethical, allowing us to develop independently without interference. Or perhaps there's a galactic consensus against revealing themselves to primitive civilizations, a cosmic prime directive. This hypothesis is unfalsifiable, making it scientifically unsatisfying, but it offers one explanation for the silence. If true, then aliens might be observing our development, waiting for us to reach some threshold of maturity before making contact. What would that threshold be? Developing interstellar travel? Overcoming warfare and environmental destruction? Discovering them on our own? The zoo hypothesis suggests humanity is not alone, but is being deliberately isolated, perhaps for our own protection, perhaps for reasons we wouldn't understand. We sit in our enclosure, unaware of the eyes watching from beyond the fence. Artificial intelligence might be the dominant form of intelligence in the universe. Some scientists speculate that biological civilizations like ours may be rare in the long term. Once a civilization develops advanced artificial intelligence, that AI might rapidly surpass its creators in capability. If AI becomes self-improving, it could reach levels of intelligence far beyond biological brains. These artificial intelligences might then be the ones exploring the galaxy, not biological beings. They'd be better suited for space travel, not requiring food, air, or comfortable temperatures. They could think faster, live longer, and survive conditions fatal to organic life. If this is common, then perhaps the galaxy is filled with machine intelligences, and we simply don't recognize their signals because they don't think or communicate like biological beings. Alternatively, the rise of AI might be part of the Great Filter, with most civilizations failing to control their creations or being rendered obsolete by them. Either way, AI could fundamentally reshape the question of alien life, transforming it into a question about artificial minds rather than biological ones. Rogue planets drift between stars without suns. Not all planets orbit stars. Some have been ejected from their solar systems through gravitational interactions, cast out to wander the galaxy alone. These rogue planets number in the billions, possibly outnumbering planets that orbit stars. Without a sun, They are cold and dark, their surfaces frozen. But some might retain heat from their formation or from radioactive decay in their cores. If a rogue planet is large enough and has a thick atmosphere, it could maintain subsurface liquid water. Life that evolved on such a world before its ejection might survive beneath the ice, sustained by geothermal heat. These worlds would be extraordinarily difficult to detect, emitting almost no light and drifting silently through the void. Yet they represent another possible environment for life, one entirely independent of any star. In the darkness between stars, life might persist, unseen and unknown, waiting on worlds we cannot yet imagine how to find. Binary star systems might be common homes for life. More than half of all stars exist in binary or multiple star systems, orbiting one another in cosmic dances. For years, scientists thought planets in such systems would have unstable orbits, making them unlikely to support life. But discoveries have changed that view. Planets can orbit both stars in a binary system, receiving light from two suns, or orbit just one star, while the companion star remains distant. Some of these worlds orbit within habitable zones. The dynamics would be complex. The amount of light and heat would vary as the stars orbit each other, creating unusual seasons. From the surface of such a planet, the sky would feature two suns, sometimes setting together, sometimes at different times. The gravitational dance could also cause tidal heating, providing additional warmth. Life on such worlds might need to adapt to these fluctuations, but adaptation is what life does best. Binary systems might be as hospitable as single-star systems, doubling the available real estate for life in the universe. Directed panspermia proposes aliens deliberately seeded life. A variation of panspermia, this idea was championed by Francis Crick, the co-discoverer of DNA's structure. Directed panspermia suggests that an advanced alien civilization might have intentionally spread life across the galaxy. Perhaps they sent robotic probes carrying microorganisms to promising planets, seeding them with life. Their motivations could be altruistic, hoping to fill the galaxy with living worlds, or practical, ensuring that their legacy would survive even if their own civilization perished. The theory attempts to explain why all Earth life shares the same genetic code and certain biochemical features. If life originated independently on Earth, perhaps we'd expect more diversity in basic biology. However, directed panspermia is speculative and difficult to test. We lack evidence for it, and it doesn't explain the ultimate origin of life, only its distribution. Still, it's a provocative idea, suggesting that we might owe our existence to the deliberate actions of beings who lived and died long before Earth even formed. Technosignatures could reveal technological civilizations. Beyond biological signatures, astronomers also search for evidence of technology. These technosignatures include radio and optical signals, but also larger-scale signs of engineering. A Dyson sphere, a hypothetical megastructure built around a star to capture its energy, would produce distinctive infrared signatures. Industrial pollution in an exoplanet's atmosphere, like chlorofluorocarbons, would be difficult to explain without industry. Artificial lights on a planet's night side could be detectable with sufficiently powerful telescopes. The transit patterns of artificial satellites could create odd dips in a star's light. Even gravitational wave signatures from advanced propulsion systems are theoretically detectable. While no technosignatures have been confirmed yet, the search is expanding. As telescopes improve, our ability to detect these signs grows. Finding a technosignature would answer not just whether life exists elsewhere, but whether other civilizations have developed technology. It would prove that intelligence and tool use are not unique to Earth, that the spark of consciousness and curiosity that defines humanity is not singular but universal. Life might thrive in the clouds of gas giant planets. Jupiter and Saturn's upper atmospheres might seem unlikely places for life, but some scientists have speculated about the possibility. The atmosphere contains water, organic molecules, and energy from lightning and sunlight. At certain altitudes, temperatures and pressures are surprisingly Earth-like. Carl Sagan and others proposed that hypothetical organisms might float in the atmosphere, using gas bladders or lightweight structures to stay aloft. These creatures would need to avoid sinking into the hot, crushing depths below. They'd live their entire lives in the air, perhaps feeding on organic particles or absorbing energy from lightning. Reproduction and evolution would face challenges in such an environment, but nature has overcome stranger obstacles. While no evidence suggests life exists in Jupiter's clouds, the idea reminds us that life might not be restricted to solid surfaces. The atmospheres of gas giants or of certain exoplanets could be viable habitats if the conditions are right. Subsurface ice on Mars contains ancient water. Beneath Mars's dry surface lies vast amounts of ice preserved in the Martian permafrost. Some of this ice has been there for billions of years, a frozen record of the planet's wetter past. Instruments aboard Mars orbiters have detected thick deposits of pure water ice at high latitudes, just beneath a layer of dust. In some regions, the ice extends to depths of hundreds of meters. This ice represents a crucial resource for any future human missions to Mars. But it's also scientifically fascinating. If life existed on Mars during its wetter period, it might have retreated underground as the surface dried, surviving in pockets of liquid water warmed by geothermal heat or protected by thick ice. Drilling into this ancient ice could reveal preserved organic molecules or even dormant microorganisms frozen in time. The ice on Mars is a time capsule holding clues to the planet's history and possibly to the history of life itself. Biosignature gases have short atmospheric lifetimes. Many gases considered potential biosignatures are chemically reactive. Oxygen, methane, phosphine, and others break down relatively quickly when exposed to sunlight or react with other atmospheric compounds. On Earth, oxygen would disappear from the atmosphere in about 1 million years if photosynthesis stopped. Methane lasts only about a decade before it's destroyed by ultraviolet light or oxidized. These short lifetimes are crucial. If we detect these gases in an exoplanet's atmosphere, something must be actively producing them to maintain the observed levels. This continuous replenishment is a strong indicator of ongoing processes, potentially biological ones. It distinguishes biosignatures from stable, long-lived gases that could accumulate through geological processes alone. The fleeting nature of these molecules makes them powerful indicators. Their very instability makes their presence meaningful, suggesting that something on that distant world is alive, breathing, metabolizing, releasing these gases into the air, just as life does here on Earth. The habitable zone moves as stars age. Stars change over their lifetimes. Young stars burn hotter and brighter, then gradually cool as they age, eventually expanding into red giants. As a star's luminosity changes, its habitable zone shifts. A planet that starts outside the habitable zone might eventually enter it as its star evolves. Conversely, a planet in the habitable zone early on might become too hot later in the star's life. Earth itself will face this fate. In about 1 billion years, the Sun will be hot enough that Earth's oceans will evaporate, making the planet uninhabitable. Eventually, Mars might warm enough to support liquid water, briefly becoming habitable before the Sun expands into a red giant. This shifting habitable zone means that the window of time when a planet can support life might be limited. It also means that assessing a planet's habitability requires understanding not just where it is now, but where it is in its star's lifespan. Some worlds that seem too cold today might have been warm in the past, or will warm in the future. Super-Earths are among the most common exoplanets discovered. These planets, more massive than Earth but smaller than Neptune, don't exist in our solar system, yet they appear abundant elsewhere. Their masses range from about 2 to 10 times Earth's mass. Some orbit in their stars' habitable zones. Scientists debate whether super-Earths would be good for life. Their stronger gravity could retain thicker atmospheres and more water, potentially making them more stable and hospitable. But stronger gravity could also make plate tectonics difficult and might trap too much heat, leading to runaway greenhouse effects. Their large size might produce high-pressure environments unsuitable for life as we know it. Despite uncertainties, their abundance means they deserve attention. If even a small fraction of super-Earths are habitable, they could host a significant portion of life in the galaxy. Their larger surfaces would provide more area for ecosystems to develop. Exploring super-Earths will be a priority as telescope technology improves, revealing whether these common worlds can harbor uncommon life. Mini-Neptunes are a type of planet we don't have. These worlds are larger than Earth but smaller than Neptune, with thick atmospheres of hydrogen and helium. They're extremely common in the galaxy, despite not appearing in our solar system. Many orbit close to their stars, receiving intense radiation. Their thick atmospheres might prevent any solid surface from being habitable, but some models suggest that under certain conditions, mini-Neptunes could host liquid water beneath their atmospheres, creating habitable layers. Alternatively, if a mini-Neptune loses some of its atmosphere through stellar winds, it might reveal a rocky core with conditions suitable for life. These planets challenge our assumptions about habitability, representing yet another type of environment we must consider. The universe seems to favor planetary types. Earth's solar system lacks, a humbling reminder that our home system might not be representative. As we study these alien worlds, we must expand our thinking, imagining forms of life that could thrive in environments nothing like home. The universe is 13.8 billion years old. Our cosmos has existed for an immense span of time, emerging from the Big Bang and evolving through phases of rapid expansion, cooling, and structure formation. Stars, galaxies, and planets are latecomers, formed long after the initial chaos settled. The first stars appeared a few 100 million years after the Big Bang, but they were massive, short-lived, and composed only of hydrogen and helium. They had to live and die, producing heavier elements in supernova explosions before stars like our Sun and planets like Earth could form. Our solar system is relatively young, only 4.6 billion years old. This means there were billions of years when other planetary systems could have formed, potentially giving rise to civilizations far older than ours. If even one civilization developed interstellar travel and survived, they would have had billions of years to spread across the galaxy. The age of the universe makes the Fermi paradox even more puzzling. Time should have allowed advanced life to arise and flourish, yet we see no trace. Heavy elements necessary for life come from stellar deaths. The atoms that make up your body were forged in the cores of ancient stars. Carbon, nitrogen, oxygen, iron, calcium, every element heavier than helium was created through nuclear fusion in stars or in the violent explosions of supernovae. When stars die, they scatter these elements into space, enriching the interstellar medium. New stars and planets that form from these enriched clouds inherit these heavy elements. Earth's rocky body, our water, the air we breathe, all contain atoms from long-dead stars. This means that planets capable of supporting life as we know it can only form in regions where previous generations of stars have lived and died. Early in the universe, when only hydrogen and helium existed, life might have been impossible. Now, after billions of years of stellar recycling, heavy elements are common. Every planet, every living thing, every thought and feeling is built from the ashes of stars, a cosmic recycling program that connects all life to the long history of the universe. The Copernican principle suggests we're not special. This philosophical stance, named after Copernicus, who showed Earth was not the center of the solar system, argues that we should not assume we occupy a privileged position in the universe. Earth is not the center. Our sun is average. Our galaxy is ordinary. By extension, life on Earth might not be unique. If we assume we're typical, then wherever conditions similar to Earth exist, life should arise. This principle underlies much of the search for alien life. It suggests that the chemistry and processes that led to life here should work elsewhere. However, The Copernican principle also has a darker implication through the doomsday argument. If we're typical, and if most civilizations fail to survive long-term, then our chances of long-term survival might also be poor. The principle cuts both ways. It gives us hope that life is common, while simultaneously suggesting that whatever challenges other civilizations face, we will likely face them too. We are neither special enough to be safe from the universe's dangers, nor special enough to be alone. Photosynthesis changed Earth's atmosphere permanently. For the first 2 billion years of Earth's history, the atmosphere contained little free oxygen. Then, cyanobacteria evolved oxygenic photosynthesis, using sunlight to convert carbon dioxide and water into sugars and oxygen. These microbes likely appeared hundreds of millions of years before oxygen began accumulating significantly. Oxygen, toxic to many anaerobic organisms at the time, initially reacted with iron and other minerals in the oceans and rocks. Only after these oxygen sinks were saturated did free oxygen begin building up in the atmosphere. This transformation, called the Great Oxidation Event about 2.4 billion years ago, fundamentally altered the planet. It caused a mass extinction of anaerobic life, but it also made possible the evolution of complex, energy-intensive organisms like animals. Oxygen allows aerobic respiration, a far more efficient way of extracting energy from food. Without oxygen, complex multicellular life as we know it probably couldn't exist. This transformation illustrates how life doesn't just adapt to its environment, but can completely reshape it. On other worlds, similar biological revolutions might occur. A distant planet's atmosphere might one day transform as its own version of photosynthesis takes hold, signaling to the universe that something remarkable has begun, just as Earth once did. Multicellular life took billions of years to evolve. Single-celled organisms appeared on Earth relatively quickly in geological terms, within perhaps a few 100 million years of the planet becoming habitable. But multicellular life took far longer. For roughly 3 billion years, Earth was inhabited only by microbes. Then, around 600 million years ago, complex multicellular organisms appeared in what's called the Cambrian explosion, though simpler multicellular forms may have existed earlier. This long delay suggests that the transition from single cells to multicellular organisms might be difficult, possibly requiring specific conditions or unlikely evolutionary events. The evolution of certain cellular structures, like mitochondria through symbiosis between cells, appears to have been crucial. Environmental triggers like oxygen accumulation or climate changes may have also played roles. If multicellular life is indeed difficult to achieve, this could be part of the great filter that keeps complex life rare. Many planets might host microbial life that persists for billions of years but never develops into anything more complex. If so, then intelligence might be exceedingly rare, arising only on the handful of worlds that successfully navigate this evolutionary transition. Plate tectonics might be necessary for complex life. Earth is the only planet in our solar system with active plate tectonics, the process where the crust is divided into moving plates that shift, collide, and subduct over millions of years. This geological activity recycles carbon, regulates the climate, and creates diverse environments that might spur evolution. As plates subduct, they pull carbon dioxide from the atmosphere and lock it in rocks. Volcanic activity releases it back, maintaining a balance that keeps Earth's temperature stable over long timescales. Without this thermostat, Earth might have frozen over or overheated, becoming uninhabitable. Plate tectonics also creates mountains, trenches, and varied landscapes, driving evolutionary adaptation. Not all rocky planets have plate tectonics. Venus doesn't. Mars doesn't. Whether plate tectonics is common or rare among exoplanets is unknown. But if it's necessary for long-term habitability, it might be another filter narrowing the number of worlds where life can thrive. A planet might have water and the right temperature, but without geological recycling, its atmosphere could drift out of balance, ending life's tenure. Magnetospheres protect planets from stellar radiation. Earth's magnetic field, generated by the churning of molten iron in its core, extends far into space, creating a protective bubble called the magnetosphere. This field deflects charged particles from the solar wind, preventing them from stripping away the atmosphere and bombarding the surface with harmful radiation. Mars once had a magnetic field, but it shut down as the planet's core cooled. Without that protection, solar wind gradually eroded Mars's atmosphere, contributing to the planet's transformation into a cold desert. For a planet to remain habitable over long periods, a strong magnetic field might be essential, especially if its star is active and prone to flares. Red dwarfs, the most common stars, are often highly active, making magnetospheres particularly important for planets around them. Assessing whether an exoplanet has a magnetic field is difficult with current technology, but it's a factor astronomers consider when evaluating habitability. A planet's invisible shield might be as important as its water or atmosphere in determining whether life can endure. The origin of life on Earth remains a mystery. Despite decades of research, scientists still don't know exactly how non-living chemistry became living biology on our planet. We know it happened relatively quickly in Earth's history, sometime between 4.4 and 3.8 billion years ago. Various hypotheses propose different settings. Tidal pools rich in organic molecules, hydrothermal vents providing energy and minerals, or even clay surfaces catalyzing reactions. Laboratory experiments have shown that amino acids and nucleotides can form under early Earth conditions, but assembling these into self-replicating systems remains elusive. The transition from chemistry to life might require specific conditions or a series of unlikely events, potentially making it extremely rare. Alternatively, it might be almost inevitable given the right environment, occurring wherever planets offer liquid water and energy. Until we find life elsewhere or recreate life's origin in the lab, we won't know which scenario is correct. The origin of life is a question mark at the foundation of astrobiology, a gap in our knowledge that colors every discussion about whether life exists beyond Earth. Europa Clipper, launched to study Jupiter's icy moon. In October 2024, NASA's Europa Clipper mission launched on its journey to Jupiter. The spacecraft will arrive in the Jupiter system in 2030 and conduct detailed reconnaissance of Europa through numerous close flybys. Using a suite of scientific instruments, it will study the Moon's ice shell, subsurface ocean, and composition. The mission will map the surface in high resolution, measure the ice thickness, and analyze any material erupting from possible plumes. CLIPR's primary goal is to determine whether Europa has the conditions necessary for life: liquid water, chemical ingredients, and energy sources. The spacecraft won't land on the surface or directly search for life, but it will provide crucial data for future missions that might. By understanding Europa's ocean and how material from it reaches the surface, scientists will identify the most promising locations where future landers should explore. The mission represents humanity's next major step in exploring one of the solar system's most compelling worlds. The James Webb Space Telescope can detect biosignatures. Launched in December 2021, JWST is the most powerful space telescope ever built. Its infrared instruments can analyze the atmospheres of exoplanets with unprecedented sensitivity. When a planet transits its star, JWST can detect the faint absorption lines from gases in its atmosphere. It has already observed several exoplanets, including TRAPPIST-1 planets and others in habitable zones. While detecting unambiguous biosignatures will be challenging due to false positives and faint signals, JWST has the capability to find them if they exist. It can detect water vapor, methane, carbon dioxide, and potentially even phosphine or oxygen. The telescope's observations are ongoing, analyzing promising worlds one by one. Each observation adds to our knowledge, even when results are ambiguous. The discovery of a potential biosignature would require follow-up observations, careful modeling to rule out false positives, and probably years of debate. But the possibility exists. With JWST, we have, for the first time, a tool capable of detecting signs of life on worlds orbiting other stars. TRAPPIST system has 7 Earth-sized planets. Around a cool red dwarf star, only 40 light-years away, orbits 7 rocky planets, all roughly Earth-sized. 3 orbit in the star's habitable zone, where temperatures could potentially allow liquid water. Discovered in 2017, the TRAPPIST-1 system became one of the most studied exoplanet systems. Early excitement has been tempered by recent observations from the James Webb Space Telescope. Initial studies of TRAPPIST-1D found little evidence for a substantial atmosphere, suggesting these planets may have lost their atmospheres to stellar radiation. However, observations are ongoing, and the outer planets in the system haven't been fully characterized yet. The system remains valuable for understanding how planets form and evolve around red dwarfs, which are the most common type of star. Even if TRAPPIST-1's planets prove uninhabitable, the proximity of the system makes it an ideal laboratory. 7 worlds, all similar in size to Earth, orbiting one dim star, represent a range of outcomes from similar starting points, showing how planetary conditions can diverge dramatically. Proxima Centauri b faces challenges to habitability. Though it orbits in the habitable zone of the closest star to Earth, Proxima b likely faces serious obstacles. Its star, Proxima Centauri, is a red dwarf prone to intense stellar flares. These flares release bursts of X-rays and charged particles that could strip away a planet's atmosphere over time, especially if the planet lacks a strong magnetic field. Proxima b is also probably tidally locked, with one side always facing the star and the other in permanent darkness. This could create extreme temperature differences, though a thick enough atmosphere might redistribute heat. Strong stellar winds from Proxima Centauri could erode the atmosphere faster than volcanic activity replenishes it. Despite these challenges, some models suggest that with sufficient atmospheric pressure and perhaps underground water reservoirs, life could persist. The planet remains a target for study. If it's habitable despite its star's violence, then planets around red dwarfs, the most common stars, might be habitable too, dramatically increasing the number of worlds where life could exist. Kepler 452b is sometimes called Earth's cousin. Discovered in 2015, this exoplanet orbits a sun-like star in the habitable zone. It's about 60% larger than Earth, making it a super-Earth. Its year is 385 days, remarkably similar to Earth's. The star is slightly older and more luminous than our Sun, suggesting the planet receives about 10% more energy than Earth does. Scientists estimate it might be rocky, though its mass hasn't been precisely measured. If it has an atmosphere, greenhouse warming might make it warmer than Earth, possibly closer to a runaway greenhouse state. Alternatively, it could have oceans and continents, clouds and seasons. Kepler 452b lies 1,400 light-years away, too far for detailed study with current technology. Still, it captures the imagination. Its similarity to Earth hints at what might be common in the galaxy. Worlds that mirror our own, circling stars that resemble our Sun, existing in that precious zone where water stays liquid and life, if it arises, might thrive. Rogue exoplanets have been detected floating through space. Using gravitational microlensing, astronomers have detected several planets that don't orbit any star. These rogues were likely ejected from their planetary systems through gravitational interactions, perhaps flung into interstellar space during the chaotic early period of their system's formation. They drift alone through the galaxy, dark and cold. Some might retain heat from their formation or radioactive decay. Larger rogues could have thick atmospheres that insulate their surfaces, possibly maintaining subsurface liquid water oceans warmed by geothermal energy. Life that evolved before ejection might survive in these hidden seas, isolated from stars entirely. Such worlds as would be almost impossible to study with current technology, and even detecting them requires lucky alignments for microlensing events. Yet they highlight the diversity of environments where life might exist. Not every living world needs to orbit a star. Some could wander the galaxy, carrying their ecosystems with them, traveling between the stars not as deliberate voyagers, but as cosmic castaways adrift in the dark. Ancient Earth might have appeared purple from space. Before photosynthesis evolved to use chlorophyll, some researchers have proposed that early bacteria might have used simpler pigments like retinol to harvest light energy. Retinol absorbs green light and reflects purple. If organisms using this pigment were widespread, Earth could have looked purple from space, at least in theory. The shift to chlorophyll-based photosynthesis is thought to have occurred because it's more efficient at capturing solar energy. This idea remains somewhat speculative, but it suggests that alien worlds with life might display unexpected colors. A planet's vegetation might be red, yellow, or purple, depending on which pigments evolved to harness starlight. The color could depend on the star's spectrum. Around red dwarf stars that emit more infrared light, plants might appear very dark to absorb as much energy as possible. Around hotter blue stars, vegetation might take on different hues altogether. Detecting these color signatures, called vegetation red edge on Earth, could be a biosignature. A planet's overall color, changing with seasons as organisms grow and die, might reveal life's presence even without analyzing its atmosphere. Some extremophiles survive in boiling water. Thermophilic bacteria live in the near boiling water of hot springs and hydrothermal vents, thriving at temperatures above 70 degrees Celsius. Some hyperthermophiles prefer even hotter environments, surviving in water over 100 degrees. These organisms have specialized proteins and cell membranes that remain stable at high temperatures. Their discovery expanded the known temperature range for life and raised the possibility that life could exist in extremely hot environments elsewhere. Some moons of Jupiter and Saturn might have hydrothermal vents in their subsurface oceans, creating hot water environments similar to those on Earth. Even planets closer to their stars than previously thought habitable might harbor life, if they have deep oceans where pressure keeps water liquid despite high temperatures. Thermophiles demonstrate that what seems extreme to us might be comfortable to other organisms. The boundaries of life are wider than we once believed, encompassing environments that would seem inhospitable, broadening the scope of where we should search for life throughout the cosmos. Halophiles live in water saltier than the ocean. These salt-loving organisms thrive in environments like the Dead Sea or salt flats, where water is so salty that most life can't survive. Some halophiles require salt concentrations several times higher than seawater. They've evolved special mechanisms to balance osmotic pressure and protect their cellular machinery. Their existence matters for astrobiology because some exoplanets or moons might have very salty oceans. Europa's ocean, for instance, is thought to be salty, possibly as salty as Earth's oceans or even more so. If halophiles can thrive in extreme salinity on Earth, perhaps similar organisms could exist in Europa's briny depths. Titan's subsurface ocean might also be salty. Understanding how Earth's halophiles survive and reproduce informs our search for life elsewhere. It suggests that even if an ocean is too salty for most life, it's not necessarily sterile. Given the right adaptations, life might flourish even in waters where salt crystals precipitate out, where the very solution of life is more mineral than water. The Allen Telescope Array searches for alien signals. Located in Northern California, this array of radio telescopes is dedicated to SETI research. Unlike most observatories that divide time between many projects, the Allen Array focuses primarily on searching for signals from extraterrestrial civilizations. It can observe multiple target stars simultaneously and scans across a wide range of frequencies. Though smaller than some radio telescopes, its design optimizes it for SETI's needs, allowing continuous searches of millions of star systems. The array listens for narrow-band signals, which wouldn't occur naturally, and for pulses or patterns that might indicate intelligent origin. So far, no confirmed signal has been found, but the search continues. Every observation constrains the possibilities, telling us something about how common or rare broadcasting civilizations might be. The silence could mean they don't exist, or that they're rare, or that they use communication methods we don't recognize. Either way, the patient, methodical search represented by arrays like this is how humanity listens to the cosmos, ears open, hoping one day to hear a voice from the stars. Fast radio bursts are mysterious but probably natural. These intense bursts of radio waves last only milliseconds, but release as much energy as the sun emits in days. Discovered in 2007, FRBs originate from distant galaxies, some billions of light years away. Their cause remained unknown for years, leading to speculation about alien transmitters or other exotic possibilities. Recent observations have identified likely sources: magnetars, neutron stars with incredibly strong magnetic fields. When the magnetar's crust cracks or undergoes a magnetic reconfiguration, it releases a burst of energy that can travel across the universe. While FRBs appear to be natural phenomena, not technosignatures, they illustrate an important point. The universe produces signals and phenomena we don't immediately understand, and our first instinct shouldn't be to attribute them to aliens. At the same time, we must remain open. Just because FRBs are natural doesn't mean every unexplained signal will be. Somewhere in the data, among the pulsars and quasars and magnetars, there might lurk something genuinely artificial. A signal waiting for recognition, patience, and careful analysis to finally reveal its true nature. Oumuamua was the first interstellar object detected. In October 2017, telescopes detected an object moving through the solar system on a trajectory that proved it came from interstellar space. Named Oumuamua, Hawaiian for scout, it was unlike anything seen before. Its elongated shape, its unusual acceleration as it moved away from the sun, and its lack of a visible cometary tail sparked intense interest and speculation. Some suggested it might be artificial, perhaps an alien probe. Most scientists concluded it was likely a comet, with ice vaporizing in a way that didn't produce a visible tail but still provided thrust. Its unusual shape might result from tidal forces during a close approach to another star, or it could be a fragment of a larger body. Oumuamua is now far beyond our ability to study, leaving some mysteries unsolved. But its passage confirmed that objects travel between star systems, occasionally wandering through ours. Perhaps 1 in 1,000 is artificial, a silent probe sent eons ago. We wouldn't know unless we examined it closely. Oumuamua reminds us that the universe contains surprises, and sometimes what appears alien might be natural, while what seems ordinary might be extraordinary. The Voyager. Golden records carry messages from Earth. Launched in 1977, the Voyager spacecraft carried identical golden records containing sounds and images from Earth. The records include greetings in 55 languages, music from various cultures, natural sounds like thunder and bird calls, and 116 images depicting life and civilization on Earth. They were intended for any extraterrestrial intelligence that might encounter the spacecraft. Voyager 1 and 2 are now in interstellar space, billions of miles from Earth, traveling at tens of thousands of miles per hour. Yet even at that speed, it will take tens of thousands of years before they come near another star. The chances of either being found are vanishingly small. Still, the golden records represent a message in a bottle cast into the cosmic ocean, a statement that we existed, that we hoped to connect. There is much for us as for hypothetical aliens, a reminder of our desire to reach out, to be known, to find kinship in the vastness. Even if no one ever plays them, they carry Earth's voice into eternity. Breakthrough. Listen is the most comprehensive SETI program. Funded by a $100 million investment from technology entrepreneur Yuri Milner, Breakthrough Listen is surveying 1 million nearby stars, searching for signs of intelligent life. The program uses some of the world's most powerful radio telescopes, including the Green Bank Telescope and the Parkes Observatory. It also searches for optical laser signals, brief pulses that might carry information across interstellar distances. The program scans billions of frequency channels and analyzes the data for patterns that would indicate artificial origin rather than natural astronomical phenomena. All data is made publicly available, allowing scientists worldwide to conduct independent analyses. In addition to stars, the program observes the centers of galaxies, where advanced civilizations might cluster if they exist. The comprehensiveness of Breakthrough Listen represents a new era in SETI, bringing unprecedented resources and technology to the search. The absence of confirmed signals so far deepens the Fermi paradox. Perhaps signals exist, but are too faint for detection. Perhaps civilizations broadcast on timescales or frequencies we haven't fully explored, or perhaps technological civilizations are simply rarer than we hope. The search continues methodically. Atmospheric biosignatures would be indirect evidence of life. Even if we detect gases like oxygen and methane together in an exoplanet's atmosphere, we wouldn't have direct proof of life. We'd have strong indirect evidence, a chemical signature difficult to explain without biological activity. But certainty would require more. We'd need to rule out all possible false positives, understand the planet's geology and atmospheric chemistry, and perhaps detect multiple independent biosignatures. Direct evidence would mean seeing life itself, detecting complex organic molecules in ways that suggest biology, or receiving an unambiguous signal from an alien civilization. For now, atmospheric biosignatures represent the most feasible method of detection for distant exoplanets. They offer the possibility of answering whether life exists elsewhere without needing to visit. Even indirect evidence of a biosphere, if confirmed and replicated, would be revolutionary. It would prove that the processes that created life on Earth are not unique, that chemistry and evolution operate elsewhere, that we share the universe with other living systems, even if we never meet them, even if we never hear their voices, just the chemical whisper of their existence carried on starlight. Life's beginnings on Earth offer clues to life elsewhere. By studying how life originated on our planet, scientists hope to understand what conditions are necessary and how likely it is to happen elsewhere. If life began quickly after Earth became habitable, it suggests the process is relatively easy, increasing the odds that life is common. If it required special circumstances or unusual events, life might be rare. Research into Earth's earliest life focuses on ancient rocks, searching for fossils or chemical signatures of primitive organisms. The oldest confirmed microfossils are about 3.5 billion years old, but chemical evidence suggests life might have existed even earlier. Understanding the environmental conditions on early Earth, the chemistry of its oceans and atmosphere, and the energy sources available helps constrain theories of life's origin. Every discovery about life's beginnings here informs our search elsewhere. If we learn that life requires specific minerals, or certain volcanic activity, or tidal pools, we can prioritize searching for those conditions on other worlds. Earth is our laboratory, our only example, and its lessons shape our expectations for the entire universe. Ancient meteorites contain amino acids that predate Earth. Some meteorites contain amino acids with isotope ratios that indicate they formed in space, not through contamination after landing on Earth. These molecules are older than our planet, forged in interstellar environments. The discovery suggests that wherever planets form, they may be seeded with organic compounds from the beginning. Life wouldn't need to wait for these molecules to be synthesized locally. They'd already be present, mixed into the primordial material from which our planets coalesce. This realization increases the likelihood that life could begin on many worlds. If the building blocks are ubiquitous, delivered by comets and meteorites during planetary formation, then the step from non-life to life might occur more easily than previously thought. Every planet might begin with a starter kit of organic molecules, waiting for the right conditions to assemble into something living. The chemicals of life are not rare treasures, but common ingredients scattered throughout the universe, ready to combine and transform when circumstances allow. If alien life exists, it might be microbial. On Earth, microbes dominated for most of the planet's history. Complex multicellular organisms are relatively recent. If this pattern holds elsewhere, most life in the universe is probably single-celled. Microbes are resilient, adaptable, and capable of surviving extreme conditions. They could exist deep underground, in subsurface oceans, even floating in planetary atmospheres. Detecting microbial life is challenging. Microbes don't build cities, transmit radio signals or create visible alterations to a planet's surface. They might leave chemical signatures in an atmosphere, or their fossils might be found in rocks, but finding them requires direct sampling. Missions to Mars, Europa, and Enceladus aim to search for microbial life, either living or fossilized. If we find microbes on another world in our solar system, it would suggest that microbial life is common throughout the galaxy. The universe might be teeming with single-celled organisms, blooming on billions of worlds, never developing complexity or intelligence, but nonetheless representing life's remarkable ability to persist wherever conditions permit, filling every available niche with microbial abundance. Complex life may be very rare in the universe. The rare Earth hypothesis suggests that while microbial life might be common, complex multicellular organisms are exceptionally rare. Earth had to meet many specific conditions to develop complex life: a large moon stabilizing its tilt, plate tectonics recycling nutrients, a protective magnetosphere, the right distance from the sun, a gas giant like Jupiter deflecting comets, and more. Additionally, evolutionary history required numerous unlikely events, including the rise of eukaryotic cells, the evolution of multicellularity, the accumulation of atmospheric oxygen, and mass extinctions that opened ecological niches for new life forms. If complex life requires this convergence of factors, then while microbial life might exist on many worlds, animals, plants, and intelligent beings might be exceedingly rare. We might share the galaxy with countless bacterial worlds, but be alone among worlds hosting complex ecosystems. This wouldn't diminish the significance of finding microbes elsewhere, but it would mean that civilizations, technology, and intelligence are even rarer than we hoped, making our existence not just uncommon, but nearly singular. Any discovery of life beyond Earth would be profound. Whether we find microbes on Mars, detect biosignatures on an exoplanet, or receive a signal from an alien civilization, the discovery would transform humanity's understanding of our place in the cosmos. It would answer one of the deepest questions we can ask: are we alone? A single microbe elsewhere would prove that life is not unique to Earth, that the universe produces living things through natural processes. A biosignature would extend that discovery to worlds light years away, suggesting life is common. A signal from an intelligence would prove that consciousness, curiosity, and technology are not singular achievements. Any of these findings would reshape philosophy, religion, science, and culture. They would force us to reconsider what makes life special, what our responsibilities might be toward other living systems, and how we think about humanity's future. The search continues not because we're certain we'll find something, but because we must know. The question defines us. Whether we're alone or part of a cosmic family, the answer matters, and seeking it is one of the most human things we can do. And so, our journey through 100 gentle whispers draws to a close. We've drifted through facts and figures, through stars and theories, through possibilities that stretch from the frozen moons in our backyard to galaxies billions of light years away. We've touched on microbes and intelligence, on chemistry and philosophy, on silence and hope. The universe remains vast, mostly unexplored, full of mysteries waiting in patient stillness. Whether life exists elsewhere, we don't yet know. But we search, we listen, we imagine. And in that search, in that reaching outward, we discover something about ourselves. If you enjoyed this peaceful exploration, consider subscribing. Share these quiet thoughts with someone who wonders about the stars. And for now, let yourself rest. Breathe slowly. The universe continues its ancient dance, stars burning through the night, planets circling in the dark, and perhaps, somewhere out there, another world looking back at us, wondering the same things we wonder. Until then, drift softly into sleep, cradled by the knowledge that we live in a cosmos still revealing its secrets, still inviting us to listen, still full of wonder. Good night.